Welcome to our 11th lectures of flexible SAE transmission system fax devices. We have in previous lecture number 10, we have discussed actually the principal operations of the shunt compensations, equal area criteria and the stability issues. Now we shall see what are the devices available to compensate this shunt compensation or the fax devices. Today actually we shall discuss the shunt compensator based on the thyristors. Thyristor is really well fitted into our fax devices because of its actually high power rating, high current rating and very simple principle of operation. Even though it is a hub control switch, you can turn it on, you cannot turn it off. It is generally naturally commutated. So, today we shall discuss three type of shunt compensator, thyristor based shunt compensator. These are namely TCR, that is called thyristor control reactor. Another is actually thyristor switch reactor, or we can abbreviate as TSR. Or there is another version of the thyristor controls reactor, that is called segmented TSR, and also we have thyristor switched capacitor or TSC. So, we shall see this principle of operations and its topologies in next few minutes. Now, little brief introduction about the TCR, that is thyristor control reactor. Thyristor control reactor is a basic building block of SVC, that is static var compensator. We can have a STATCOM and SVC, so we have to find it out that where it should be applied. So, for the static var compensator, we will find a different kind of topology, and if it is SVC, there actually the static var compensator finds its usefulness. TCR is used mainly to absorb excess of the reactive power into the system. Generally, we will see the switching and we will see that how it will absorb the extra reactive power into the system, and thus it improves this actually power factor and other related issues to the power quality. Generally, it cannot be used alone because of the inductive nature of the power system load, and most of the loads are drives based, and since these are inductive in nature, it is normally used with a thyristor switch capacitor to provide the controlled reactive power generation. So, we shall see to it that why it is alone not competent enough to actually enhance the capability of the power transmission. We require a support of the TCSC with the TCR to effectively utilize the power handling capability of the line. Single phase thyristor controlled TSR is consisting of a fixed, or generally this is a lower power rating air core reactor inductance L, and with the bidirectional thyristors it is connected in the anti-parallel fashion. Let us see its topology. So, generally it is connected it is a shunt device. So, ultimately you can control the current depending on the switching angle of these thyristors, and generally thyristors are available with a quite high rating and of 4 kV or 10 kV. Most of the cases actually there is a factor of safety for 6.6 kV 10 kV voltage rating of thyristor is chosen, and of the current rating of 3 kiloampere or 10 kiloampere. So, that is a standard rating available with the thyristors, and we need not have to series or parallel any of the thyristor, you can directly fit into this configuration. and sometime to meet the required blocking voltage and the current real power system, where it is a it has to handle the power in the range of the thousands of the megawatts or megavar, then series parallel connections of the thyristors are used, and these are called the thyristor valves. See, in Hingorani book you will find that few case studies where actually few megavolt of the power handling capabilities TSR has been reported. Thyristors valve can be brought through by conduction by simultaneous application of the gate pulses of all the thyristor of the same polarity. So, we can put into the operations, and there is actually a factor of safety, because if the one thyristor is on, see if it is considered the, we have studied in a power electronics that this what are the problem associated with the actually series operation of the thyristor. If one thyristor is on, another thyristor is not on, then voltage stage goes to the actually off thyristors, and that can damage. And for this reason properly voltage balancing network is required to be placed, and all those things who have been put for, and these have been put into the system, that is called basically the thyristor valve. Now, let us talk about thyristor control reactor. So, it can, what is the advantage of it? Advantage of it that it has very high voltage rating, since it is made of thyristors, it can block very high voltage. So, it can be established by connecting thyristors in series and giving synchronization of the pulses, so that it can turn off and turn on, and so this can be operated for a very high value of the voltage blocking capability. Same way thyristor can be put into the parallel, and that can increase the current handling capability. It can be established by the parallel connection of the thyristor valve and with giving the synchronous pulses, and it is will be simultaneously on the parallel path of the thyristors. Valve will automatically block immediately after zero crossing. So, we will have a natural commutation, and unless it is reapplied. So, reactive power absorbed by TCR is proportional to the current flowing through these circuits. So, for this reason more current flow through the circuit, I into omega L will be the voltage, and proportional var will be actually absorbed here. The current in the reactor can be controlled maximum thyristor close to 0 to the open, that is 180 degree, alpha equal to ticketing angle equal to 180 degree, and by this method, that by method of actually firing delay angle. Generally in this case, the TCR is actually is operated in the range of 90 to 180 degree. So, this only then only it will absorb the reactive power, and it cannot be operated 0 to 90 degree, since it is a normal, actually we have studied that is that will be behaving like a basically simple converter. So, for this reason we will actually operate it 90 to 180 degree, and it cannot be varied. In case of the AC regulator, it is varied from 0 to 180 degree, but it will be should be varied to 90 to 180 degree. We shall see the expressions of it, and from there we can actually understand why it is not possible to vary actually 0 to 90 degree at all, rather it has to be operated in the second quadrant 90 to 180 degree. Now, let us understand the waveform. Since this current, we have told you that alpha required to be 90 degree. So, and it is compensating the inductive current. So, definitely it will have a phase lag of 90 degree. So, of course, since there is a phase lag of the current by 90 degree, so alpha can start after only 90 degree. So, thereafter you will give a delay, this value is alpha, that it will start conducting for the period of the sigma. So, from there we can calculate what should be the value of the current and how much reactive power is been absorbed or produced. As reported earlier, that current in the reactor can be controlled from the maximum to 0 and by changing the delay angle or the firing angle. The closure of the thyristor valve is delayed with respect to the peak of the applied voltage. Please understand that it has to give a 90-degree phase shift, and since in inductor current actually lags by 90 degree, so it should be 90-degree lagging, and thus the duration of the current is in a conduction mode can be controlled. So, this is the waveform for the positive cycle and this is the waveform for the negative cycle. So, this is the positive negative peak. So, here the current will start, actually the waveform, but you give a delay angle alpha. So, ultimately this will be the amount of the conduction. So, we can calculate that what is the value of L here, since Vt is equal to Vm cos omega t and during positive half cycle. So, you are adding IL, which is a function of the delay angle, will be 1 by L alpha to omega t. Ultimately this become Vm by omega L, that is nothing but a XL, that is the impedance of this line, into sin omega t minus sin alpha. So, this equation is valid for omega t, varied from alpha to pi minus alpha. And so, we can find out that from this expression there is an offset current, that value is minus Vm sin alpha, because there will be a term associated with it. And of course, this value will be the same if alpha equal to 90 degree, then basically this will be 0. So, similarly it is followed from the negative half. Thus, this value basically will give a shift across the x axis. So, this is the actual current. So, if you change the angle alpha, this is alpha, so it will start like this. So, this area is the offset that is given by Vm by omega L into sin alpha, and similar equation is followed into the negative half cycle. So, what is the takeaway from here? The delay angle is definitely here alpha, and that conduction is actually the angle sigma, sigma is actually 2 pi minus alpha. Thus, as the delay angle increases, correspondingly increasing the effect of the result in the reduction in the conduction angle of the thyristors or valve, and as a consequent the reduction of the reactor current through these devices. At maximum delay, that means alpha equal to pi by 2, offset reaches the maximum value, that is what I was saying, that value actually Vm by XL sin alpha, if sin alpha is 90, then that value is maximum. That value is Vm by omega L, at which both the conduction angle and the reactant angle become 0. So, it does not absorb any power. It should be noted that these two parameters, the delay angle alpha and the conduction angle sigma, are equivalent. Therefore, TCR can be characterized either of them, because there is a relation between alpha and sigma. So, you can write it in terms of alpha or you can write it in terms of the sigma. So, what happened here? This is a voltage curve for firing angle equal to alpha equal to 0 degree, and this will be the current, it will be almost touching the 0, because but since there is a no pure inductance, so it will be actually, though it is almost 0, yes it is at 90 degree. So, this will be the current to the TCR at alpha equal to 0. So, how it will change for different values of alpha? So, you will have that actually from there will be a delay of 30 degree either side. So, it will be chopped in either of the sine wave. So, you will get this kind of waveform. So, thus you can calculate its RMS value and thus power, reactive power, whatever the calculations, you will find that it is changing according to the conduction angle or the firing angle. So, same way this is for the 45 degree. Now, let us see by continuous firing angle, if you gradually change the firing angle, sometimes it is required to damping purpose mostly. So, what happened, we have start with alpha equal to 0. So, in first half cycle you get it here, thereafter you introduce a small delay, that is alpha equal to alpha 1, and thus you get this current. Similarly, you change to alpha 2 little more, so you get this current. So, what happen, you can dynamically control the power required by the reactive power in every cycle by changing the alpha. So, accordingly you can actually see that this is the current, and ultimately what basically this current comes out to be? This current comes out to be this. So, gradually it is damping, it can act as a damper. So, let us do the mathematical analysis of this current profile. The reactive current, let us consider the positive half cycle, that is given by I L omega t is Vm by omega L sin omega t minus sin alpha, where alpha is less than omega t and greater than omega t and less than actually pi minus alpha. Otherwise, omega t's value will be equal to 0. So, let us do the Fourier series analysis. So, we can write the Fourier series and we assume that there is a symmetry, thus all the actually value of a1 to an will be 0 and we do not assume any DC component, and thus Bn can be all the B1 will be given by the fundamental of it will given by this. So, from there we can find that B1, we can do these calculations and will be 2 by pi Vm by omega L, that is by XL, that is pi minus 2 alpha by 2 minus half sin alpha. So, let us substitute it in B1, that is the fundamental of IL1. So, essentially what you will get, it is 2 by pi Vm by omega L 2 pi minus 2 alpha by 2 minus half sin alpha into sin omega t. So, thus fundamental current of TCR is given by Vm by omega L 1 minus 2 alpha by pi 1 by pi sin 2 alpha. So, you can find that how it is changing. So, ultimately what you can see here, what you can see here, this value at 90, what will be value at 90? Let us substitute here 90. So, it is 180 degree. So, this value is essentially is 1. So, it is 1 by pi, and here you will find and there will be a minus sign that will make it plus, and ultimately here it will be again, it is actually pi and pi will cancel out, ultimately essentially you will get the value to be 0. So, this is the value of the peak current, and accordingly this value will change for different values of alpha. This is the expressions of the peak current in case of the thyristor controlled reactor. So, what should be the admittance of it? So, this is the expressions of the current, and so ILP1 is the function of alpha is Vm into Bl, where actually BTCR, B suffix TCR, that is basically the abbreviation of TCR, is the admittance of the TCR. So, we can see that can be also implemented in terms of the firing angle alpha. So, where Bl will be given by Bl max 1 minus 2 alpha by pi, same way, where the maximum value is definitely will be given by omega into XL, and otherwise this value will change. Now, we can now the expression of the admittance in conductance angle, you can change it. So, sigma equal to, you know that actually where alpha equal to pi minus sigma by 2. So, from there if we can substitute, so Bl will be Bl max sigma by pi minus sin sigma by pi. This will be the expressions for the instantaneous value of the Bl for the angle, for the firing angle alpha or conductance angle sigma. So, you may require to calculate, so what should be the amount of the impedance you will be injecting to the system or admittance injecting to the system, whatever it may be. So, from there we can calculate that this should be the value of the admittance. So, what happened, we can rewrite this equation, the fundamental current of this TCR equal to Vm into Bl, where Bl will have this kind of relations, Bl equal to Bl max 1 minus 2 alpha by pi minus 1 by pi sin alpha. So, what happen if we increase the alpha? Effect of increasing alpha will be TCR admittance will be reduced, and thus what happen, IL alpha 1 will be reduced and reactive power absorbing capability will be reduced. If you decrease the alpha, then what will happen? Then this admittance will be increasing and value of IL1 will increase, thus reactive power absorbing capability of the TCR will be increased. So, we can see that what are the advantage and disadvantage of it. If you increase alpha, then as current decreases, power handling capability decreases. So, it is actually inversely proportional with the alpha, and if alpha is increases, reactive power is absorbed, more reactive power is absorbed. So, by varying alpha, smooth control of the reactive power absorptions is achieved with the help of the TCSCR. So, this is the one of the advantage of TCSCR. What are the actually advantage? It is a very simple circuit, and paralleling of thyristor is quite proven technology for past 40 years, and it is thyristor based, and since it is naturally commutated, you need not have to do much, and it has a huge power handling capability, and it is very simple operation. You change the alpha and you get a direct reaction to it. Increase the alpha, you get actually reduced reactive power, you actually decrease the alpha, you get enhanced enhanced absorption of the reactive power. So, these are the main takeaway from this TCR. Now, let us see that actually the graph wise how it will work. So, this is the current value plotted in x axis, plotted in y axis in terms of the alpha, and this is the degree. So, alpha equal to 0 you get 1, and ultimately you will have what happen, this is the value of this part, and this part corresponds to this. So, you will have a actually 1 minus 1 by pi sin 2 alpha will have this contribution, and this will have a linear contribution with alpha. If you change alpha, this part will have a linear contribution. So, here what happened, this will actually contribute less and this will be contributing more. So, at 45 degree, and gradually what happened at 90 degree, this value reduces to 0. So, in that way actually by changing the value of the alpha, this value of the inductor current changes in this way. So, what is a thyristor control so, in practice what happened, the maximal magnitude of the applied voltage and the corresponding current is limited by the power handling capability of the devices. That is what it is written. Current will be limited by the rating of the components. That is the thyristor valve. In practical TCR can be operated anywhere in defined VA line. So, this is actually the maximum value of the voltage blocking capability of the device, and this is the maximum current can flow into the device, and same the load line concept what we have used in case of the transistors. Same thing can be done, but here plot is actually just opposite. Here we have taken I in x axis. So, what happened here, the practically TCR can be operated anywhere in the graph, and the boundaries which is determined the maximum attainable admittance is basically this line. So, this value is basically the BL max. So, we have to choose the operating point anywhere in between. We can choose the operating point, basically it is nothing but a tan theta. So, tan theta, this theta should be less than this value, and we can simply operate the TCR. This is the actually this is all about our TCR. We continue to our lecture with different type of shunt compensated thyristor topologies. Thank you for your attention. We shall coming out in the lecture number 12 soon. Thank you.